I think you have already met Sebastian. So just to repeat, I think in the first day it was said, but let's say it again. He is from Warsaw, where he got his undergrad and his master. Then he moved to the University of Washington.
No,
to University
Indiana
of in Bloomington to Indiana, where he took his PhD with Adam Szczepaniak. And currently, he is a postdoc at University of Washington in Seattle. Okay. As we have seen, part of his research here is an expert in scattering theory, field body physics, lattice QCD, and so we look forward to his colloquium. As I said, you don't need to rush. We have time.
Okay.
I think everybody's flying out tomorrow or something like that.
So you can.
So we have plenty of time.
Can go for all my backup slides. Okay, thank you very much. Welcome to lecture number 5. Fortunately, I'm young and inexperienced, so I cannot prepare. I'm unable to prepare a colloquium that's sort of simple and the flow is so nice as Andre. So this will be extremely technical, incomprehensible. To sort of ease the pain of listening to this colloquium, I put asterisks on the titles of slides that I consider technical. So when you see an asterisk and you're afraid, just close your eyes. Okay, and what I'm going to talk about is actually quite complex. We're moving from scattering of 2 to 2 to scattering of 3 to 3 states. And as you'll see, it involves a lot of complications, a lot of beauty, if you consider complex analysis beautiful, and a lot of opportunities for students like yourself to get engaged in some cutting-edge research in this area. So the goal of my colloquium really will be to explain this single plot, but in the meantime, I'll talk about a few other topics. Wait, I think I'll give you a lightning review of why we care about free-body interactions and why amplitude analysis is important. You probably remember that from lectures. I'll talk about the current status of so-called free-body formalisms, so the generalization of what you see on the blackboard to free particle states. And then I'll talk about analytic properties of free-body amplitudes, the topic that we all now love and appreciate. So, let us start. Why free-body physics? As I said during my first lecture, there is an enormous amount of states being discovered during the past 100 years, starting from, I believe, proton was the first hadron that was discovered. And up until now, where there's a bunch of new resonances identified every year. As you can see from this plot of LHCb, from the LHCb experiment, already in the past decade, there's been of the order of 70 new hadrons. This is not entirely accurate. You have to look at this plot with a certain dose of skepticism because, well, there are some states that, like this pentaquark, that have been sort of discovered in 2015, and then people realized that the analysis has to be refined, and the state became 2 states. So this plot doesn't really show all the new hadrons. It's sort of shown all the papers about supposed new hadrons being published, and really shows the flow of our understanding about strong interactions. Now, many of those states, as I said, as I'll show in the next slide, are difficult to identify because the line shapes and properties of cross-sections are extremely complicated. And many of those states decay to free-body final states. The couplings to those states make the analysis more complicated, so we need to somehow understand that. Of course, I also should mention that there are more experiments than LHCb. There's BESS3, that's sort of studying is charmonia and tetraquarks. And there are many more experiments that I mentioned during the first lecture. Now, the complication of that comes from free body states, intermediate states, and in general from sort of exotic states discovered nowadays. This can already be visible on the plot of mass spectrum of so-called standard charmonia. So charmonia was one of the most, so CC bar states, according to quark model, were considered one of the most successful examples of the quark model. Why? Because charm quarks are very heavy, and you can actually justify using non-relativistic potentials to describe them, something like the so-called famous Cornell potential, which has a Coulombic part and linear part responsible for the so-called quark confinement. And if you put this type of potentials, maybe refined with some spin-spin interactions, you can beautifully explain the spectrum of many low-lying charmonia. See that there are predictions of quark model and then experimental predictions with some nice widths in the plot. Until you start reaching all these different excited thresholds, where DD mesons, DD star mesons, D plus star, etc., start coupling to your QQ bar states, and you start seeing all these different QQ bar-like states that are not necessarily predicted by the quark model. And this is maybe not surprising, but this is a warning that we can't really treat mesons that we find in this naive picture of quark model. Or in other words, if we compare this plot to the spectrum of E plus E minus of positronium in QED, which is a system that you can study perturbatively because of weakness of QED coupling, you will see that the agreement is indeed only for the slow states. Later, all the mess turns on, and we need more refined analysis. Why is it difficult to study those states? Because if you look at some cross sections, that's more or less how they look like. You see some bumps, a lot of complications, a lot of noise, a lot of strange structures, a lot of thresholds that open, as you remember from the lectures. Thresholds correspond to some branch point singularities that can affect the cross sections. And some states that are shown on this sort of exclusive cross section are not even visible as bumps. You need to study more other reactions more carefully to identify them. So that justifies the need for a careful amplitude analysis. So something I was trying to teach you during the lectures. And this amplitude analysis must incorporate free body states. Free body states can mimic things like Bright-Wigner peaks in your scattering cross sections. Here's a nice example from the COMPASS experiment where they studied free pion final reactions, and in certain article said, well, we see this bump that we identify as this new state A1-1420. And then people came, said maybe if you consider a model where before the final decay there is this intermediate free kaonic state where these free kaons can go on shell, this, in the language that I taught you during the lectures, leads to a so-called Landau singularity. So some additional singularity in your process that might enhance the cross-section. Maybe if you do consider this model, you can explain this state without the need for additional pole, additional bump in the cross-section. And you see that TS model, so triangle singularity model, is almost indistinguishable from the Bright-Wigner. So how do you know that you have a triangle singularity or a genuine pole in your process? That's a question that needs to be answered by a careful amplitude analysis. If you study systems like candidates for tetraquarks, the ZC3900 state that I also mentioned during the lectures that can be, for example, visible in this J-psi pi mass distribution, you can study some coupled channel scattering amplitudes, and again, either mimic the data with some Bright-Wigner bump or with triangle singularity, and there's very little difference because the data is noisy and not entirely precise. You can have many different models that give you good chi-squared in your fit, but they lead to completely different structures in the unphysical complex Riemann sheets that you would like to identify as your pole singularities. Okay, so back to basics. Quick review from the lectures. We need model-independent, unbiased understanding of scattering amplitudes. We go back to fundamental principles, analyticity, unitarity, crossing, Poincare symmetry. We use these principles like unitarity to constrain our amplitudes, and we learn something about the singularities in the complex plane. So what we see here is some kind of amplitude on the first Riemann sheet. We see a bump, and we know from unitarity that this bump corresponds to the opening, that this discontinuity here corresponds to opening of the two-body intermediate state or opening of the two-body threshold channel. And the bump that we see here might be a manifestation of a pole on the second Riemann sheet. So if we know about this discontinuity of the amplitude, we can continue to the second Riemann sheet, which is, as I said during the lectures, glued to the first Riemann sheet, and see the resonance as a pole there. Okay. Using other principles like crossing, we can classify the singularities of the amplitude. Well, unitarity tells us that we have all these right-hand cuts. They can be related to two-particle thresholds, three-particle thresholds, etc. Also can be related to some more complicated singularities, like one-particle exchanges in the free-to-free scattering, which I'll mention. From crossing, we have these left-hand cuts that correspond to some virtual one-particle exchanges that you can model, for example, within some EFTs. We can have bound state poles, and because the amplitude is defined on several Riemann sheets, we can continue to these Riemann sheets and, for example, study the behavior of the poles with some coupling strength parameter, see how these bound states become resonances or the other way around, or just identify both bound state and resonances in the amplitude. Here's a picture that I promised you during the lecture, how we can imagine these two Riemann sheets connected to each other. The blue one is the first sheet. In the upper half complex plane, we can dive to the second sheet, which is in the white color, and then if we go around, we will emerge back in the lower half plane on the complex plane on the first sheet again. So this is more or less how you could imagine how they are glued together. This is a non-relativistic example in the energy plane, not in the Mandelstam S plane. If you have more channels, again, as I told you during the lecture, you can imagine these Riemann sheets as half spheres glued together. If you have more than more than one channel, like two channels, then you have 4 Riemann sheets because you have 2 square root singularities. So you have 2 to 2 Riemann sheets. You can imagine they are a torus. If you have 3 channels, you have 8 Riemann sheets, and so on and so on. You can imagine them being some more complicated topology. But they are just one entity on which your scattering is defined. Okay, important tool in this amplitude analysis is the K-matrix parametrization. Just to remind you, K-matrix is an object that appears in the denominator of the partial wave projected amplitude. It contains all the dynamical information about our model. Phase space fixes imaginary part of the inverse of the amplitude. And what I offer here is a much quicker derivation of the K-matrix parametrization from the so-called Cayley transform. Every Hermitian operator can be written in terms of, every unitary operator can be written in terms of Hermitian operator. It's symmetric, that's real if S is symmetric. And from that, by remembering what's the definition of transition operator in terms of S, you can immediately derive that the transition operator must have this form in terms of this K operator. So, excuse me? Symmetric with respect to exchange of incoming and final states, yes. Yes, there's time reversal. Well, in strong interactions. Yes. Okay. So just to remind you what the K-matrix is. I was talking about experiments, but this unbiased model-independent way of studying amplitudes based on these fundamental principles is also extremely useful in lattice QCD, which Amy taught us about. Quick reminder what lattice QCD is. We discretize continuum QCD in an Euclidean space. We put in finite volume. We write the partition function in terms of new variables, which are our gauge links and discretized fermions. And then we apply Monte Carlo simulation techniques to essentially treat this quantum field theory as a statistical problem. And what we use this partition function for is to extract correlation functions. Correlation functions that, if we want to study, let's say, two-body states or three-body states, would be objects, matrix elements of some products of operators that create two or three body hadrons, three or two hadrons in the incoming state, annihilate them in the outgoing state, and using the spectral decomposition of this correlation function and the large time dependence of this correlation function, we can extract energies of those hadrons. And of course, this is not a simple thing to do. You need to create a lot of Monte Carlo samples, so gauge configurations. You need to study systematics, dependence of your spectrum on volume, of the discrete finite spacing, dependence on the quark masses, which are physical, etc. There is some noise, statistical noise associated with your simulation, etc. But eventually, if you put a lot of hard work into this, you will extract those energies. But as Andrew mentioned, those energy levels are not the resonances that you are looking for. Resonances are poles of the scattering amplitude on unphysical Riemann sheets. So these energies is not what will tell you what's the spectrum of QCD. At least not entirely. But fortunately, Lucier in 80s came up with a brilliant idea that we can use the volume dependence of the spectrum to extract the information about scattering parameters. This is, again, what we have on board. We have exactly this equation here, although I wrote it in terms of the K-matrix and probably used a slightly different definition of F. But essentially, what you can show is that the infinite volume two-body K-matrix satisfies a certain condition, determinant condition. If you find zeros of this equation at certain energies, finite volume energies, you can constrain this two-body K-matrix, and you can use many different models to make a prediction about the scattering amplitude or compute scattering amplitude from lattice QCD spectrum. This F is the known function that's essentially some integral difference of some propagator or double propagator, so something that Andrew taught you about. And this determinant is a condition in the angular momentum space of incoming and outgoing states. Of course, angular momentum in finite volume box is not conserved, so these two angular momenta will be different in general. And there's been a lot of work on this type of problems. Here I will show you more or less how the workflow looks like. You identify the energy spectrum in your box. You study many different volumes. You study many different irreducible representations of the little groups of the cubic group, because again, in box, you don't have rotational symmetry, so you don't have well-defined J quantum number, but you have well-defined irreducible representation of the cubic group. And you compute a bunch of spectra from your correlators, you plug them to this Lucier formula, and you can extract scattering amplitudes. Or what you actually do, you come up with many different models, and you constrain these models using this formula. And what you get is some predictions for the amplitudes with some error bars associated both with statistical noise from energies and, for example, systematics from many different model choices. Once you have your models, you can analytically continue your amplitudes to the complex plane and identify poles corresponding to resonances that would be physical resonances if you used a physical pion mass. Here, this paper that I'm showing you, considered from HADSPEC, considered pion mass of 400 MeV. But in principle, the same procedure can be used at any pion mass. One more plot, analytic continuation. This was a coupled channel study of pi-pi, eta-eta, and kk-bar systems. You have many Riemann sheets here shown in the complex momentum plane. This is relative kk-bar momentum plane. And you can see that you try many different models, you analytically continue them, they correspond to many different poles, you take average over those poles, and that's your final result. So now let's switch gears and move to free particles. In the case of free particles, the workflow would be, the philosophy is almost identical, it's just a little bit more complicated. What you do, you start with finite volume calculation. You come up with your operators that will allow you to extract 2 and 3 body energy levels. You get them in different EREPs of cubic group. You use a quantization condition, so-called free body quantization condition, that has very similar form to the 2-body quantization condition, but has this object called K3. This is the free body matrix element of this K-matrix operator that I introduced earlier. And it has a slightly different special function, F3, that contains both the 2-body K-matrix and also this 2-body F object. Using this quantization condition, you can constrain this 2-body and 3-body K-matrices and compute amplitudes. But now your amplitudes are not given by a simple partial wave projected K-matrix parameterization that you showed on one of the first slides. They are given by an integral equation. Because when you add more particles, there are more variables, energy conservation doesn't fix the integration, or doesn't reduce the number of the integrations over intermediate momenta in the derivation of K-matrix parameterization, and you end up with an integral equation. And it's a little bit more complicated than that. The amplitude that you get also depends on 8 kinematical variables, which you can think of like 8 Mandelstam variables rather than 2 Mandelstam variables. So when you start thinking about analytic continuation, you need to choose which variables to complexify and so on. And eventually you figure this out and you get resonance poles. That's the workflow. Okay, so a little bit about free body kinematics. The only purpose of this slide is to show you that it's complicated. You have 3 things coming in, 3 things coming out. These 3 things that come in can be divided into so-called per spectator objects. So essentially you can try to understand your free body states and quasi 2-body states, but the problem is that 2 particles in a pair can have non-zero relative angular momentum, so it's now like quasi 2-body scattering for particles with spin. And the problem is that the spins of particles are defined in their respective center of momentum frames, which is different than the total center of momentum frame for free body states. So in addition to describe in addition to all these complications, when you want to describe your scattering by performing some kind of higher number of variables partial wave projections, you need to perform boosts from pair states to center of mass states, and it becomes very messy. But in general, it's not impossible to do this. You write your amplitude, free body amplitude, as 9 different pair spectator amplitudes. You perform some kind of partial wave projections in the pairs angular variables and the relative pair spectator angular variables, and you can reduce the number of variables required to describe the scattering process from essentially 8 to 3, because you reduce angular dependence, just like in the 2-body case. So what you end up with is an amplitude that depends essentially on some angular momenta of intermediate states of the incoming state and outgoing states in pairs. the total angular momentum J, and on free energy-like variables, which you can consider to be invariant masses squared of pairs in the intermediate and outgoing state, and the total invariant mass or total energy. Looks pretty complicated. Once you perform this decomposition, you can start thinking about derivation of your finite volume quantization condition. The idea of the derivation is on this board. It's exactly the same idea. It's here. It's just that you need to include the fact that there are free body intermediate states in the problem, which means that there will be some singularities coming from on-shell free particle propagation. There will be some free body beta-salpeter kernels involved, as also two-body beta-salpeter kernels in the two-body subchannels. But also very important is to notice that there will be single particle exchanges between two disconnected two-body beta-salpeter kernels, and this one particle exchanges are this important novelty of the free body physics that I highlighted yesterday when I was discussing free body unitarity. There's this special diagram that describes on-shell propagation, so physical propagation of one exchange particle between two body subprocesses. If you take care of all these different singularities that emerge from on-shellness of intermediate states, you can essentially repeating steps that you did with maybe a little bit more combinatorics, derive this quantization condition that's now a determinant, written as a determinant, is in higher dimensional space because in addition to angular momenta of pairs, it's also a determinant over momentum of a spectator. Then another part of this formalism are these integral equations. So it's easy to think about these integral equations as following from the free body unitarity for per spectator amplitude, just like two-body unitarity implies your K-matrix parametrization. You can find a parametrization of the scattering amplitude per spectator scattering amplitude that's also implied by the free body unitarity. Now, it takes a form of an integral equation. This integral equation depends on these blobs attached to pair lines. So these are two-body scattering amplitudes. And it also depends on the integration kernel. The integration kernel contains this one particle exchange amplitude. This is a piece that is required by free body unitarity. And then there is some unknown dynamical function that is real, that is an analog of the two-body K-matrix, and we call it a free-body K-matrix. Here in the intermediate loop, the integral is performed over the momentum of the intermediate spectator, or equivalently over the invariant mass of the intermediate pair. And schematically, you can write it like this. In order to identify what your free-body amplitude is, you need to know what are the interactions in the two-body subprocesses or subchannels. You need to know what this kernel is that describes long-range one-particle exchanges and short-range free-body interactions. Now, again, to simplify comparison with what's done in the two-body case, if we amputate or remove these two-body amplitudes from external states, and compare it to the two-body K-matrix parametrization, which can be written in this form, you will see that there is a clear analogy. We have free-body amplitude, two-body amplitude. This B object plays a role of two-body K-matrix, but it has additional imaginary part that's not present in the two-body K-matrix because of this one-particle exchange. Then there is some phase space, which can also appear from intermediate two-body states in the two-body case, which can also appear in the free-body case, but it's some free-body phase space. Now, we also need, in the free-body case, include the possibility of two intermediate particles in a pair to interact. That's why the two-body amplitude enters here. Here, it doesn't appear. And we need to integrate because the energy momentum conservation in the intermediate free-body states does not uniquely fix the energy and momenta of individual particles, but it does in the two-body intermediate state. That's why there is no integral here. Okay. So here's a quick slide on the status of the formalism. These steps of deriving quantization conditions and integral equations for many different systems were done in these different papers. So you can see name Sharp is attached to all these papers, or almost all these papers, because it's really a driving force behind development of this program. You could ask yourself a question, well, why do you need to derive new formalism for every individual case, particles with spin, two particles that are different, one particle that is different than the other two, and so on and so on. As you saw on the previous slides, these free body considerations can become very complicated, and surprisingly, when you add a little new detail that seems trivial, you immediately discover, oh, it's not so trivial. Any new complication makes it even more complicated, so that's why you need a new paper for every new case considered. The formalism is, I would say, almost ready to cover any case of interest with almost stressed. There is not too much on the front of implementation, and especially implementation to the actual lattice QCD free body levels. There are some example from HADSPEC, scattering of free pions in the maximal isospin. There are some examples of studying A11260 system from George Washington University group and friends. There is very recent paper on the omega meson by Yan et al. But that's more or less about it. Maybe there's one more paper on studying lattice QCD spectrum. Sorry, I'll take that back. Not lattice QCD, 5⁴ theory spectrum in a box. But that's not lattice QCD. A brief lightning explanation on some particular example, how this workflow looks like. This is a project that we're working on right now. It should probably be ready in 1 or 2 months. Essentially, a study of free light meson in a box, 2 counts, 1 pion, or 3 pions, 3 counts, 1 count, 2 pions, at maximal isospin. Why maximal isospin is important? Because the system is weakly interacting, not in a sense of electroweak interactions, but in a sense that there are no resonances that develop strongly when you consider maximal isospin systems. The novelty, or maybe the importance of this study, is that we consider these particles at physical pion mass. And, well, what you do to get the scattering amplitudes is you construct your... Sorry? Yes, there's no QED included here. No, yes. No, there are no bound states, no resonances. I mean, this study is really, as I said, we are just starting computing some states in a more or less systematically controllable manner. This field started like about 10 years ago, and a lot of theoretical complications that had to be understood and sort of resolved. So, and implementation is another level of complication. So we're studying from the simplest systems where energy spectrum almost looks like non-interacting energy spectrum, so that we have good control over what we're seeing. Going back to this slide, you construct operators, get correlation functions, study their time dependence, and you get a point, an energy level. This is spectrum of 3 counts at physical pion mass in many different irreducible representations of your rotation group of a cube. You take these different energy levels, you plug them to the 2-body or 3-body quantization conditions that allows you to constrain using some, for example, effective range models, values of scattering parameters. And for 2-body subsystems, like scattering lengths of pi k, for instance, or this 3-body K matrices, for which you also have to write some kind of parameterization. One that is commonly used is so-called threshold expansion. And once you figured out what are these two-body and three-body K matrices, you plug them to integral equations, and you compute amplitudes, scattering amplitudes of 3 to 3 mesons. In this particular case, this is a scattering amplitude of 3 pions colliding in a very simple sort of spatial configuration where their momenta form equilateral triangle, and then outgoing pions also form equilateral triangle, but the reaction planes can be at some angles to each other. And you can compute the amplitude, which is this is real and imaginary part of 3 pions to 3 pions amplitude. You can compute the full amplitude, which is this red band. You can compute the amplitude that is driven just by the one particle exchanges. So you set your free-body K matrices to 0. You can compute the amplitude that includes this free-body exchanges with some special type of final and initial state two-body rescatterings, and you can plot it. You get an amplitude that you can probably never extract from an experiment. Here is a plot of amplitude squared for these 3 different systems. See some sort of chiral suppression of the amplitude when you add a pion to the system. The free count to free count amplitude is much larger. And the main takeaway for you from this slide is that it can be done, including partial wave projections, etc., computation of integral equations, extraction of spectrum, and so on and so on. The meaning of this number is that your one particle exchange amplitude drives the whole process, and it diverges when you get to the threshold. Yes. The other 2 are fixed by this particular configuration of momenta. So if you take them to form an equilateral triangle, energy fixes invariant masses of pairs. Yes, we're fixing all momenta to some configuration, and we're just plotting this, because otherwise making 3-dimensional plots and making Dawid's plots, which is another idea, doesn't really tell you what's going on, because you don't see anything on the Dawid's plot. I mean, what you see on the Dawid's plot is OPE. Okay. So now, once you understand the workflow, the general idea, beautiful complications. So I told you one particle exchange diagram is special. It leads to a lot of non-trivial problems and a lot of beauty in the study of free particle scattering. And I'll like to give you some physical example. So let's talk about a state that exists, was discovered, and has caused a lot of interest in the hadronic spectroscopy community. This is this doubly charmed tetraquark. So essentially a state that has 2 charmed quarks. So it has been discovered by LHCb in the vicinity of this DD star and DD pi thresholds. And you see that there are these free-body thresholds, and TCC is sort of found as a bump above them, a very narrow bump, which means it lives relatively long. But because it's above the free-body threshold, you can guess that it's on the unphysical sheet related to the free-body threshold, not to the two-body threshold. So it's a genuine, at least that's how I like to think about it, it's a genuine free-body resonance. And inclusion of free-body effects is very important when you try to determine properties of TCC from the data. In this particular study, the authors shown that if you perform analysis that does not include this one particle exchange diagram, you will get a width of this TCC state that's 2 times too large, or 2 times larger. And the goal, the dream, given the context of the previous several slides, would be to compute this state from lattice QCD. So how would we do that? Now, because TCC is so close to the decay thresholds, when you increase the pion mass, what happens? D star, rather than a d pi resonance, becomes a bound state. These two thresholds become inverted because now d star d has lower energy than d pi state, and TCC travels from the Riemann sheet associated with free body threshold to the real axis below the d star threshold and becomes a bound or a virtual state. So this is what happens to TCC when you start increasing the pion mass. This has been seen by many lattice collaborations, that you discover TCC as a virtual state if you apply Lucier formalism, perform this whole procedure that Andrew derived. And you could say, well, if at physical or heavier than physical pion mass, the TCC becomes essentially a two-body state, DD star, you can use Lucier, and there's no need to worry about free-body physics. What are you talking about? Claim is, we're still in the kingdom of this one-particle exchange diagram. Because what happens when you start increasing mass of n pi? This one-particle exchange diagram in the free-to-free amplitude corresponds to additional discontinuity on the right-hand side that essentially means or describes physical propagation, so in principle for an infinitely long time or up to infinitely long time, of an on-shell state. When you start increasing the mass of pion and d star becomes bound, moves to the, or this dd pi threshold moves to the right, the physical pion exchange becomes a virtual pion exchange because it cannot go on shell due to energy considerations. And what you study in this case, as I said, is dd star scattering, but the pion exchange becomes virtual, and it corresponds to the left-hand cut. This is one of these left-hand cuts that I told you is required by crossing, or we know they exist from crossing. Now, when you do this type of, you perform this type of reasoning, you will realize that this left-hand cut lies extremely close to the pole of the TCC tetraquark. So it might significantly affect the amplitude analysis because there is new singularity in the problem, and it will probably somehow influence how the amplitude behaves near the pole. And this is indeed what happens when people performed the initial analysis of this state using lattice data. They ignored this fact and determined that TCC appears as a virtual state. Then when this analysis was repeated by another group, including left-hand cut, you discovered that this TCC no longer is a virtual state, but appears as two sub-threshold complex poles on the unphysical Riemann sheet. There is another problem, which I don't know if Andrew mentioned during his lecture, that if you have a left-hand cut of left-hand singularity in the system that you consider, that means you can no longer apply your Lucier quantization condition to the energies lying on top of this left-hand singularity. Because the derivation that Andrew showed does not take into account power law effects that are associated with these left-hand singularities. So not only you need to consider more complicated amplitudes when these left-hand cuts appear as you increase pion mass, but you also are shrinking validity of the Lucier formalism. So now the question is, can we somehow resolve that problem using free body approach? Because the free body approach, by necessity, takes into account the presence of this one pion exchange, because it's required by the free body unitarity. And the answer is yes. If we somehow can connect this d pi state, somehow analytically connect this d pi state to the d star state, and this physical pion exchange to the virtual pion exchange, we could in principle continue our free body formalism to the region where the two-body physics is involved. Before we talk about that, we need a small introduction about integral equations. So let's consider a simple model F with zero angular momentum in all two-body and free-body channels. Let's get rid of the short-range free-body interactions, set this K-free object to 0. What it will define you is a system that's described by just one particle exchanges and two-body interactions in pairs. What I will call the resulting amplitude is D. It is given by this integral equation. Our kernel is just described by one particle exchange. If we partial wave project, this one particle exchange will have this promised singularity. It is a logarithmic singularity given by some complicated function depending on our kinematical variables. That we can, to simplify the problem, we can consider two-body interactions where the two-body K-matrix is given by the leading order effective range expansion, such that we have only one parameter that controls the whole system. There's probably no simpler free-body to free-body scattering problem that you can consider. Just to give you some intuition, if we set this two-body scattering length to 2, it will produce some deeply bound state. The threshold, energy threshold is at 2 mass, so this is 1.7 mass. If we increase two-body scattering length, this bound state, two-body bound state will become shallow. It will move closer to the energy threshold. And near the bound state pole, the amplitude will take this pole form. So as you can see, this will be our very simplified model of the tetraquark, where the bound state will be our D star bound state if the pion mass is heavy, but we're using free-body integral equations to describe this system, so we are free to set the mass to whatever value we want, such that we can consider free or two-body systems depending on our preference. The analytic connection between the two-body and free-body scattering amplitudes is given by the LSZ reduction. Essentially, the statement that follows from the LSZ reduction formula that I also mentioned during the lectures but didn't explain it, is that if you take free-to-free scattering and you take a two-body subsystem and you continue the total invariant mass of the two-body subsystems to the pole of beta-salpeter kernels that are dressing your operators or your amplitude, or in other words, to the pole of the two-body amplitude, you can extract the two-body scattering amplitude as the residue at this pulse. And the two-body amplitude, I call here phi b amplitude. Phi stands for initial particle and b for the bound state in the two-body subchannels. So the connection between two-body and free-body amplitudes can be achieved by the LSZ reduction formula. So using these free-body integral equations, we can study the system above two-body threshold, we can study the system above free-body thresholds, and we can see, can we generate something like free-body bound states in the problem? How do you solve these integral equations? Numerically, it's a very well-known technique, probably over 100 years old now. You discretize the intermediate momenta, you rewrite your integral equation as the matrix or algebraic equation, and you can solve it by matrix inversion. You can use smart techniques to speed it up, and you get some kind of bound state particle amplitude obtained from free-body integral equations. You can get some phase shift between bound state and particle. You can get plots of bound state particle effective range, scattering length as a function of two-body scattering length, which again is the only parameter that describes our system. So this is describing this part of this bottom panel. What are these orange points? Not sure if Andrew mentioned that during the lecture, but if you look at this equation, it's an equation that can be reverse engineered. You can enter energy levels from your lattice QCD calculation to extract scattering amplitude, but you can also enter scattering amplitude to predict finite volume energy levels. So if you plug a model for two-body and three-body interactions into three-body quantization condition, you will predict a bunch of free-body energy levels. Now you will see that some of those are below relevant thresholds and can be identified as particle bound state energy levels. Once you have those, which are two-body energy levels, you can plug them to two-body quantization condition to extract two-body scattering amplitude. It's a neat idea, and these are these orange points. It essentially shows consistency in this formalism. It works as it should, giving you the same result, regardless of where you start from. Oops, I should probably skip this slide, but I don't want to, because I love this slide. Close your eyes if you're scared. You want to extract free-body resonances, free-body virtual states. You need to continue your amplitude to unphysical Riemann sheets. It becomes a little bit problematic in the free-body integral equations because first, they are free-body, second, they are integral equations. Free-body means more variables and more complicated singularities. You already know that the kernel of this integral equation contains this logarithmic singularity. Depending on the values of kinematical variables that you consider, these singularities can make many different shapes in your complex momentum plane over which you integrate and cut the integration interval, original integration integral that is shown here with the yellow line. Well, so what does it mean you need to do? You need to deform the integration contour to avoid all these complicated singularities. In certain circumstances, it's impossible to deform the contour. You need to use some additional techniques, adding singularities, etc. You have to study position of the so-called domains of non-analyticity of the kernels and also non-perturbatively study the positions of singularities of the amplitude, which enter the integral in this integral equation and can contribute singularities. It becomes very complicated, but it's doable. And you can resolve the problem with singularities. Next problem is how to analytically continue. It's interesting to notice that the singularities of the solution of the integral equation are induced by collisions of some other singularities in the integration kernel with the endpoints of the integration contour. So, for example, you have two-body amplitude that contributes two-body branch cut from unitarity. In the integration kernel, this is this blue point. This blue point can collide with your integration interval. When it collides, it will generate free-body threshold in the solution of the integral equation. If you want to continue your amplitude beyond this free-body cut to the unphysical Riemann sheets, you need to use analytic continuation via monodromy, as it's called in fancy way by mathematicians. In other words, you need to choose contours that may make loops around the singularities, and that will define the solution of the integral equation on the higher Riemann sheets. If you do that, analytic continuation, let us start with something simple. You can analytically continue your solution below the threshold, and you will see that the K-matrix, or scattering phase shift, will have a discontinuity that's related to the fact that you have virtual particle exchange at certain mass. For 3 different scattering lengths, let's maybe focus on this left plot. So you will see that above the threshold, your phase shift agrees with the finite volume calculation using quantization conditions, but because of the left-hand cut, they will start diverging the infinite volume calculation that incorporates the presence of the left-hand cut and the two-body and the finite volume calculation using Lucier formalism that doesn't know about left-hand cuts. They will diverge, and you will see the breakdown of the formalism that Andrew just taught you about. But it also suggests clear resolution of the left-hand cut problem in the Lucier formalism that's relevant for this tetraquark state. Because what you can do, what you observe is that the free body integral equations give you the correct analytic structure with the left-hand cut and infinite volume phase shift. So you can use your free body formalism to replace two-body formalism and extend applicability below the left-hand cut. So how would you do this? You would just compute energy spectrum of something like your TCC. You would extract 2 and 3 body K matrices. You would solve integral equations to get the scattering amplitude, and then you would perform LSZ reduction to get the DD star scattering amplitude at the given heavier than physical pion mass. Well, I've heard I have 2 hours. Before we continue with the tetraquark, let's stick to the simple model for 20 more minutes and talk about its spectrum. So you perform analytic continuation, you can continue below the threshold, you can continue to unphysical Riemann sheets. What you will find out that the spectrum of the states form so-called, or reproduces so-called Efimov phenomenon. I'm not sure if you're familiar with what Efimov phenomenon is. It's essentially a situation in which you have three particles such that they only interact pairwise, and the pairwise interactions are very weak, even such that they don't support existence of two-body bound states in the systems. But because of this one particle exchange interactions, that's again implied by free-body unitarity, the three-body system will show an infinite geometric series of bound states. By geometric series, I mean of energies that form geometric series and whose sizes form a geometric series with the quotient given by like famous Efimov's universal constant. So this is an incredible phenomenon in the free body problem, quantum mechanical free body problem. Again, you have system of particles that interact so weakly that there's no way for two-body bound state to emerge, but you have infinitely many bound states if you just add one more particle. It's incredible, and that's what we reproduced using these relativistic integral equations. You see how the energy behaves as a function of this single parameter, two-body scattering length. We follow this state on different Riemann sheets when it evolves from something like a virtual state to a bound state, and then becomes a resonance. I'll talk about this in a moment. And all the trajectories of these states on this plot are just rescalings of each other. So there is this discrete scaling symmetry related to this geometric series. We can continue the solution to the unphysical Riemann sheet associated with the free body threshold. If we increase A, you will see that the pole from becoming a bound state, from being a bound state becomes a resonance. You see a bump. Pole enters the discontinuity and disappears, but there is a bump. If we continue to the second Riemann sheet, you will see that this bump is really a pole. And then if you start tracing how these poles behave on the unphysical Riemann sheet, you will see that they start forming cyclic trajectories on the second sheet. Now, the best way to explain that is to show you an animation. And this will highlight the beauty, potential complexity of free-body physics when you start thinking about analytic continuations of the scattering amplitudes. So what we will be doing here, we'll take some negative scattering length that's very small, such that all the poles go to complex infinities. If scattering length is very small, there is no interaction in the system, so there should be no interesting spectrum, which from analytic point of view means all the poles are at complex infinities. So the pole will start approaching the threshold as we increase our interaction strength, and then you will see what happens. So this is our pole, we increase the interaction strength, boom, what happened? Another pole appeared from the threshold out of blue. The original pole jumped to the first Riemann sheet and became a bound state. Now this one reaches the threshold, it becomes a bound state on the first Riemann sheets, moves through this threshold singularity, but another one appears out of nowhere and starts moving on this cyclic trajectory. The cyclic trajectories, as you can see, they are rescaled by Efimov constant, are very close to each other near the threshold where the system is non-relativistic, where this discrete symmetry property works. They start deviating from each other away from the threshold where the system becomes non-relativistic. Now, where do these new resonance poles appear from, and why do they appear from exactly at the energies or at values of the scattering of the interaction energy that makes the previous resonance a bound state? Well, the answer to this question has two parts. First of all, discrete scaling symmetry of Efimov problem holds for the amplitude as a whole, not just for the spectrum. So if you look at the complex plane from this perspective that the complex plane is a complicated, complex topology that consists of many Riemann sheets, the scaling symmetry of this problem holds on every Riemann sheet. The scaling property holds between amplitudes of at some open sets of these Riemann sheets and values of the amplitude at other open sets of these Riemann sheets. So it's not just a property of the spectrum. It's a more general property. For example, the scaling symmetry also holds for the residues of the poles that we consider. The second part of the answer is a free-body threshold is not associated with a algebraic branch point singularity. So it's not a square root singularity anymore. This is something I haven't mentioned during lectures because I wanted to shock you today. It's a logarithmic singularity, which means it has infinitely many Riemann sheets associated with it. And the claim is that these other missing poles are contributed to the problem each from one Riemann sheet associated with the free body threshold. So you have infinitely many Riemann sheets. One of them, due to the scaling invariance, this pattern of cyclic motion on each Riemann sheet is repeated ad infinitum on higher Riemann sheets, and each one contributes a complex pole approaching from complex infinity. It ascends to the higher sheet and then becomes Efimov bound state. Okay, I should stop now. So let me just finish with the tetraquark. You can apply these integral equations to the tetraquark. You can analyze lattice data using your solutions. The tetraquark system is more complicated because you need to consider possibility of partial wave mixing in the incoming and outgoing state. You have to use this Bloody-Biederhan parametrization that I mentioned during the lectures. So parametrization that uses two phase shift and so-called mixing angle to describe scattering. And you can come up with a very simple model that reproduces lattice data. You can analytically continue, find your TCC threshold in a model that includes left-hand cut, so there are no problems with left-hand cuts appearing like in the original lattice analysis. You can study how this TCC state moves with the changing set of parameters, for example, such as interaction strength. You will see indeed that if you perform more refined analysis with left-hand cut included, this TCC at heavier than physical pion mass will appear as a subthreshold complex pole. It can move to become a bound state. It can be a virtual state. Interesting thing happens when you play a little bit with this model, remove one parameter, make other parameters slightly larger, a tetraquark system will immediately start behaving like an Efimov state. This is a property that has been sort of suggested by many physicists during the past 20 years. States that form meson-meson molecules can, in principle, behave like Efimov states. In reality, unfortunately, probably not, because the parameters of these states are not fine-tuned enough. But it's interesting to observe that there might be some shortcut or some connection between the molecules that we study sort of in realistic analysis and this beautiful picture of Efimov states that I showed you on the previous slides. Okay, so I'll stop here. Main takeaway points is enormous progress in the study of free body states in lattice QCD. People are reaching stage when we can study maybe the simplest systems, but nevertheless we can study them at physical pion mass. We now know what kind of formalism needs to be applied, how it works. We can generate energy spectrum, we can solve integral equations, we can analytically continue them. This whole formalism mechanism seems to be ready to start analyzing interesting free body resonances. And if you start applying this heavy mathematical machinery to other problems that might not necessarily immediately be connected to complicated free body resonances, you can gain new insights about long-studied systems, for example, like Efimov states. Thank you.
Thank you. Okay, we have plenty of time for discussions and questions.
Easy, oh no.
At the end on 35, it's not one of your easy questions, it's a real easy one. Yeah, I didn't catch the different colored bands. What are these? Like the red to the yellow, what's changing?
Sorry, can you
I was just
speak
trying to
louder?
I'm trying to understand the colored lines on the plot. What is changing?
Oh, the different color. Okay, yes. So what this plot presents is solutions of these integral equations using certain guessed, very simple models that should mimic tetraquark. And different lines essentially show parameter dependence of those models. And to be more precise, they determine effective range of d pi scattering in P wave, which is really the driving subchannel that most importantly contributes to the generation of TCC. So in the two-body subchannel, we can have d pi scattering in the P wave. This is the wave in which d star resonance appears. So a pole, so something that blows up, it is large, so it contributes in a meaningful way to the free body integral equations. And well, when you change this effective range, you will get different curves. So it sort of shows you some parameter dependence. There's two different panels. One is a system where you consider no free body interactions. You need to adjust them to match lattice data.
So did you fit the results, or
no? We don't fit we didn't fit the results. No.
And so this is a demonstration that if you ignore the three body short, is that the short distance piece? Is K3?
Yes, if you ignore the short distance piece, you cannot reproduce lattice data.
Interesting. Okay, so this is a real clear demonstration of the three body term really coming in.
Yes.
Okay. Thank you.
Probably I should have mentioned, but I was being rushed.
Sorry.
No, just kidding, just kidding. No, I was very slow in the beginning.
Are there more questions? Okay, seems not. So let's thank
you.
Sebastian again.